start.
So, good morning everyone. I am Pawan Yadav. I am a PhD student working with Dr. Amit Prasad.
I am Sukrit. I am also working with Mr. Amit Prasad as a PhD student.
So, today we are going to perform direct shear test. So, this test is generally suitable for cohesionless soil or the soil which have a 30% less than 30% fine content. So, this is the thumb rule which generally we use. If the fine content is less than 30%, we will perform the direct shear test. So, generally from this test, we are going to determine the shear strength parameter. So, the shear strength parameter should be determined on for the undisturbed soil sample. So, for the undisturbed soil sample, how we will collect the undisturbed soil sample? As you all have seen, we have to collect the sample in the cell B2, and from the cell B2, we have to extract the sample, undisturbed soil sample. So, this is the sampler ring. So, what we will do? We will push this sampler ring in the cell B2 and we will get the undisturbed soil sample. But in the soil which have coarse grained soil or the soil which have very small low fine content, in such case we cannot collect the undisturbed soil sample. So for that we have to reconstitute the soil sample at the in situ density and water content. So this is the Sabarmati sand. So this is the SW type soil. So for the such type soil we cannot collect the undisturbed soil sample. So we have to reconstitute the soil sample. So here we have prepared the sample at the maximum dry density and optimum moisture content. So if anyone want to see, you can see this soil. This is the sand.
And in some cases it might happen you might not be able to do a standard Proctor test on a perfectly cohesionless soil you might have seen. Then you go for relative density test and you find the Emax, E minimum, and then you prepare the specimen at whatever void ratio you want. There are some correlations from N to relative density which we saw yesterday as well. So you can relate to find the in situ void ratio from there and then prepare the specimen using the Emax, E min values at a particular relative density.
So this is the apparatus which is required in the direct shear test. So this is the lower half and this is the upper half. So here you can see the needles. This is the base plate, and here you can see these grooves. So this groove should be fit in this needle.
We also see there are some corrugations kind of thing. So it is provided to in a way let water pass through if you are doing a drain test, or you are also allowing consolidation to happen in the first stage when you have applied the normal stress, right? So these corrugations are to allow the water to pass.
This is the porous stone. This allows the uniform passage of the water. So the water can flow from the soil uniformly, or it can go into the soil mass uniformly. So this will help uniform flow of the water. Here you can see two types of the gripping plate. So one is the solid and one is the perforated. So if we want to perform the undrained test, so we have to use this solid plate, and if you want to perform the drain test, you have to use the perforated gripping plate. So here you can see the grip. So you can see the grip. This helps to restrain the bottom and the top of the surface. So it will provide some friction so that the soil mass will not slip. And the direction of this grip should be perpendicular to the direction of the shear. So if we are doing the shearing,
so the direction of shearing would be in this direction. So these gripping plates should be perpendicular. These grips should be perpendicular to the direction of shearing, so that it can create a resistance at the base of the soil so that it does not slip at that point.
this is the filter paper. So it allows to flow only the water, and it prevent the flow of the soil particle. So it will help to flow the only water.
Next, we place the upper box and we have to ensure that it is exactly in line with the lower box because once we push the specimen in, it does not slide or it goes as we want in the while doing the test.
is the remolded or reconstituted sample which we have prepared at the OMC and MDT.
Means we will check the shear at the optimum moisture content.
No, here we are, if you want to determine the shear strength, so in situ, so you have to prepare the sample at in situ density and water content.
We prepared for now at maximum dry density and optimum moisture content just for demonstration purpose. If you want to do it at the in situ condition, that also you can do. As I said, you can relate the SPT value with the relative density value, and then what you can do is perform a relative density test from which you will be able to find Emax and Emin, and you are known with the relative density value from the SPT correlation, and then you can find the void ratio from relative density value, and then you can find what density you want to prepare the specimen.
So this is undisturbed sample, right?
This is not a
This
disturbed. This
we
is reconstituted specimen. We have prepared it at a particular density and water content.
So we have prepared this sample in this sampler ring.
If you see, there is no plastic fines or even non-plastic fines in this.
But how come it is intact? This is that sand only,
Because
no?
we prepared it at some moisture content,
Ah.
right? So there will be some suction which would be holding it.
So that moisture content is determined.
Sorry?
Known. That moisture content is
We prepared it at a known density and moisture.
So the density is 1.77 gram per cc and the moisture content is 12%.
So we ensure that the upper and the lower boxes are in line. And next thing we ensure is that this ring is exactly in line of the upper box.
Otherwise when we will push it, it will be disturbed from the side.
Can you elaborate the preparation of sample?
Yes.
That reconstituted sample.
Reconstituted.
Yes.
So what we have done, we know the maximum dry density of this soil.
Yes.
So we have calculated the dry soil mass.
Yes.
And we know the water content, so we have calculated the amount of water. We,
OMC.
we know the OMC. So we have no
Maximum dry density.
maximum dry density and optimum moisture content.
Okay.
So we know the optimum moisture, maximum dry density. So what is the maximum dry density? Gram per cc. We know the volume of this sampler ring. So we will calculate the solid mass of the solid.
Mass of the soil.
And the 12% of the mass of the solid, we will get the total weight of the water. So we will we have mixed it properly, and after that we have divided the whole soil mass in three parts. So it was coming around 314 gram. So we have divided it in 3 equal weight, and we have compacted this this soil in 3 layers. So we have marked here. This is the temper. So we have marked 3, 1, 2, 3 in 3 equal parts. So first we have compacted up to this mark, and after that consequently we have compacted in 3. Compacted by this remnant. Okay.
So we have inserted the soil specimen inside. Okay. Now we again assemble, again create the
We have to repeat the same process. So first we have to put the filter paper. After that we have to put the
upside down.
dripping plate.
That is also perpendicular.
That is
That is
the direction of steering.
This is perforated.
This is perforated.
We are doing drain test, so that why we are doing. This is the temper. This temper is temper. So I am following the most temperature.
First gripper plate, then only porous stone.
Yes.
So
The
this
soil
is,
has to come in contact with the plate, right? Then only that grip would be created.
so this is the locking screw which lock the upper and lower part of this shear box. So that while we are doing this arrangement, the sample will not be disturbed. So this is the gapping screw, so which will be used to create a gap between upper half and lower half. So why we are creating a gap? Because we are doing the shearing. So if we are not creating a gap, the shear, there will be some shear resistance due to this upper and lower half.
Friction.
Due to friction. So whatever friction we want due to only soil particle. So that's why we are creating a small gap. The size, the gap should be minimal. If we, the gap is higher, so while doing performing that while we are doing consolidation, the soil particle will come from this gap. So be careful that the gap should be minimal. It should be less than the size of the soil particle. Here you can see the small gap between upper half and lower half. Now we will put the whole assembly in this trolley.
नहीं इसको So now what we'll do is, using this wheel, we'll make the whole assembly go a little forward so that it comes in contact with the proving ring and the horizontal dial gauge, right?
While rotating, we have to see this proving ring. There should be a 1 or 2 division movement.
The horizontal dial gauge started moving, that means this is already in contact with the assembly, but not the proving ring. It's not moving, so it's still not in contact. So this would move only when this gear is at neutral condition, right? It won't move. It would get locked if it is at A or B. We'll tell what is A, B and other gears. We'll tell you about that.
There should be 1 or 2 division movement.
So just in contact should be there. Right. Okay, so we'll stop there and we'll lock it
At A position.
You might have to adjust the wheel a little bit, because to move from N to A or B, it would create. Sorry. So what you can do is, maybe you can create a 0 here and also do a 0 correction. If you observe, there is some correction to be applied when you do the plotting of your data.
So we have made a just contact with this, but for whatever this, it has already moved significantly.
It's fine. It didn't take any load, right? Because there was no resistance offered to the soil.
Load will
That's
be
fine.
transferred from this handle.
So,
because it is
so all the resistance would be provided from here, right?
Okay.
Okay, because this is the fixity, right? So there will be no resistance provided. We can move it till the proving ring is in contact. Okay.
So basically,
We'll tell. So if you see, now we have to apply the. So the first stage is to apply the normal stress. Decide the normal stress basis that from what depth you have collected your sample, right? So if you have collected your sample at a depth of 5 meters, so if you say the effective density might be 10 kilonewton per meter cube, so 10 into 5, 50 kPa would be the approximate normal stress acting at Z depth. Same we can find for 10 meter, 15 meter, 20 meters and all. So correspondingly we should apply the normal stress from where we have collected the sample, right? So now what we do is we place this loading yoke
on the top of this pressure pad. This is the cantilever loading arrangement. So we will apply the load at this cantilever,
So
and
we
it will
check
transfer the
the
soil.
horizontality of this. Okay, so we see that the bubble is at the center. That means it is at this level. Okay. Now what we do is we take this vertical dial gauge. So make the vertical dial gauge 0.
चलेगा डेमोन्स्ट्रेशन तो है अभी
It should be actually vertical. It should not be tilted. So next step is to apply the suitable normal load, and we'll measure the change in the vertical dial gauge due to that. And then what we'll do is we'll fill this box with water to simulate a submerged condition, and that is also the worst case condition in which we should test our soil specimen actually. Okay, so what we do is we apply the load. In sands the adjustment takes place very quickly when we apply the normal load, but when we fill the water we have to wait at least 10-15 minutes so that whatever consolidation has to occur would occur, and the vertical dial gauge reading would become constant. Today we will not be doing all the things in completeness, but we will go through all these steps, but you have to wait. If there is some plastic fines or some non-plastic fines which are significantly there, then you might have to wait for a longer time for the vertical dial gauge to become constant. So we apply load which would in a way give a pressure of around 50 kPa at the top of this specimen through this ball and loading pad. Okay. So whatever change occurs in the vertical dial gauge, you may please note that whenever you perform the test. And then what we do is we fill this box with water. So this would simulate a submerged condition once we allow the water to go into the specimen, wait till whatever changes occur, and we see that changes occurring through the vertical dial gauge reading. So the vertical dial gauge reading should become constant once the consolidation would occur completely.
इसमें पानी क्या जरूरत है?
किसमें?
इसमें पानी क्या जरूरत है?
किसमें? इसमें? तो नीचे से we had used the porous stone and the perforated plates. So the water would go inside the specimen and saturate it, and whatever changes would.
सैचुरेशन अगर सैंड है तो सैचुरेशन करने की क्या जरूरत है? सैंड है क्यों?
Why? Like under submergence, any soil is saturated, right?
नहीं, अगर आपको सैचुरेटेड कंडीशन में टेस्ट करना है तो how to
वर्स्ट
do
केस
it?
हो गया,
How
वर्स्ट
to do
केस,
So that's the worst case.
वर्स्ट केस.
Which we have to do.
नहीं पर डेंसिटी का क्या मतलब रहा? हमने तो अलग अपना इंस्टीट्यूट डेंसिटी पे किया, वो किया और फिर सबमर्ज कर दिया.
हाँ.
डेंसिटी तो खत्म ही हो गई फिर. डेंसिटी कैसे बची? डेंसिटी तो चेंज हो गई ना फिर तो.
So that change is occurring due to the consolidation which is there, right? So for example, if you collect an undisturbed specimen.
हमने इन सीटू डेंसिटी पे ही अपना सैंपल बनाया.
So ideally it should be for undisturbed specimen, right? When we collected the undisturbed specimen, there would have been release of stresses, right? There would be some stress history in the specimen. So whatever consolidation occurs, if you apply the same load, it would in a way be a, if you assume a oedometer test, it would be in the range less than the consolidation, the pre-consolidation stress, right? So whatever that swelling had occurred because of the release of stresses, now again that compression would occur and it would go at the same state, right? So we are trying to get back to the
simulate the same condition.
exact. So when we had taken out this specimen, there would have been some unloading as well, right? So there would be some swelling or there would be change in void ratio during that stage as well. So that's the thing. Okay. So now what we do is, before we start shearing, we ensure that the dial gauge reading, horizontal dial gauge reading and the proving ring reading are at 0. Now what we also have to decide, another important thing is the deformation rate. As sir was asking, what is the relevance of A, B gears and all. So if you see, there is a speed chart given here of the shearing deformation rate. So if you see, the maximum deformation rate you apply is 1.25 and the minimum you can apply is 0.0002 mm per minute deformation rate. So what we're doing is a drained shearing, right? So we take comparatively low deformation rate, slower deformation rate, right? And if you have even more some fines content, then you have to do a drain shearing, then you might have to go to a even lower deformation rate so that there are no development of any excess pore water pressures, right? So we are doing today on 0.25 mm per minute. So we have set the gear to A2, A here and 2 here, and now we have set all the things, and we assume that all the things would have become constant. Vertical dial gauge would also have become constant. So now to start shearing, what we'll do is we have to remove these locking screws first, which are locking the upper and the lower box. This is very important because if you don't do that, then
There will be no shear.
there would be no shearing and all the load would be taken up through these locking screws by the upper and the lower box. Okay, and also it could damage your locking screws and it can slightly bend it, so it would be very difficult for later if you have to insert it and take it out. So please take care of these locking screws. Okay, so now we had already set proving ring to start from 0, but it can happen due to some adjustments that it doesn't take load. So if there is some, like for 2-3 divisions it does not take load, so we note that and we'll apply that 0 correction later when we are plotting all our data, right?
So here you can see this sheet. So we have to take two reading. One is the vertical dial gauge reading and another is the proving ring reading. So here it is written least count of the dial gauge. So the least count of this horizontal dial gauge reading and vertical dial gauge reading is 0.01 mm. And here it is written the proving ring constant. So you can see from here.
So if you see, this proving ring has a capacity of 1 kilonewton. Okay, so we have tested it and seen that till 866 divisions it would be taking a load of 1 kilonewton. Okay, so the proving ring constant becomes 1 kilonewton divided by that number of divisions. So what we'll do is when we'll be sharing, we'll count the number of divisions and later we'll multiply it with the proving ring constant to get the load which is there.
So here it is written. Here it is written horizontal dial gauge reading. So this is the horizontal dial gauge reading. So we have to take the reading at each 20 division of the movement of the horizontal dial gauge reading. So once in this needle reached at 20 division, so we have to note the reading in this proving ring, how much division it's showing in this proving ring. Similarly, we have to note the vertical dial gauge reading. So for this vertical dial gauge reading, we have to take the reading according to time. So once start the test, we have to start this stopwatch, and for 1 minute, 2 minutes, 3 minutes, we have to take the reading in this vertical dial gauge reading. So this is the vertical dial gauge reading. From here we can take the reading and we can note in this vertical dial gauge reading roughly.
Okay, so as soon as you start sharing, you have to also start the stopwatch simultaneously so that the readings are